Shipbuilding is an exciting fusion of engineering and craftsmanship. From welding giant steel plates to launching majestic vessels, each step brings the ship to life, an inspiring journey that transforms raw materials into powerful machines ready to conquer the seas. The hull then underwent final dimensional inspections. Laser scanners compared the finished geometry to the design model, confirming that the structure was within specified tolerances. Using computer-controlled CNC plasma and oxy-fuel cutting machines, workers cut the steel plates into predetermined shapes based on digital models and blueprints. This process involves cutting not only flat plates but also more complex shapes such as frames, stiffeners, beams, bulkheads, and curved hull segments. Each cut piece is tagged and classified for identification and efficient assembly. After cutting, the plates are transferred to the forming department, where hydraulic presses and rollers are used to bend the steel to the required curvature, especially for the lower hull and bow sections. The plates are then fitted with longitudinal and transverse stiffeners, using a semi-automatic MIG/MAG welder, forming the stiffeners that will become part of the larger hull blocks. Next came modular block fabrication, with each structural block assembled on a dedicated rack or flat platform in a separate fabrication bay. Fabrication teams worked in parallel on multiple blocks, depending on their complexity. A typical block included internal partitions, floors, beams, racks, ladders, and foundations for future mechanical and electrical systems. Some blocks were equipped with through holes for piping, hatches, manholes, and cable trays. Welding sequences were carefully planned to minimize thermal distortion. Quality inspectors used ultrasonic testing and X-rays to verify critical welds throughout the process. As fabrication progressed, blocks were fitted with temporary reinforcements to prevent distortion during handling and shipping. Each completed block was then primed to protect against corrosion before assembly. Next comes the keel placement and slipway assembly. The first major step in the hull assembly is the placement of the keel block. This block is precisely placed on the Slipway 2 supports at SIMA's Callao Shipyard. This block forms the backbone of the ship and serves as the baseline for all subsequent blocks to be aligned. Reference lines for keel placement are established using a laser theodolite and alignment jigs. Once the keel is secured, the double bottom blocks are assembled on both sides. These lower blocks contain the longitudinal beams, the top plate of the hull, and the lower hull frame. Workers use hydraulic jacks to adjust the block position and maintain tolerances within millimeter-level accuracy. Multiple welds join each block edge to the previous structure, and all joints are subjected to magnetic particle testing and vacuum box leak testing. Assembling the bottom and midship blocks. As the lower hull progresses, the center blocks are lifted and lowered into the structure by gantry cranes. These blocks form the engine room space, accommodation floors, and midship structural members. Each block has been prefabricated with internal, horizontal, and vertical bulkheads. Some even include stairs, deck floors, and pre-installed pads for future equipment. Precise alignment is essential. Workers use steel wedges, clamps, and laser trackers to ensure each block fits both horizontally and vertically into the next. Once in place, the blocks are welded to adjacent blocks and inspected before moving on to the next block. The ship's midsection, comprising multiple centerline and wing blocks, took shape gradually. The hull expanded in width and depth, forming a solid steel structure along its entire length. Start with the construction of the bow and stern sections. At the same time, the bow and stern blocks are built in separate compartments. The bow blocks consist of curved plates, hull sections, and internal frames that form the forwardmost compartments such as the chain locker, bow tank, and collision bulkhead. Due to their curvature and complexity, these blocks require more shaping and careful welding to maintain their shape. The stern blocks incorporate structures for the propeller shaft tunnel, rudder base, and aft bulkhead. They also support the rudder post and part of the stern plate. Both the bow and stern blocks are staged, transported, and lowered onto the slipway when space permits. Joining these curved sections to the straight midship requires careful edge preparation and shaping to maintain a smooth flow of the hull lines. Once aligned, full penetration welds permanently join the blocks. Side and outer hull panels. Next came the installation of the side and outer hull panels. With the internal structure complete, the outer hull blocks were installed to form the outer skin of the hull. These consisted of large curved panels covering the sides from the double bottom to the weather deck. The panels were preformed and reinforced in the block assembly shop. The installation required skilled crane operation and careful adjustment. Workers used drop chains, wedges, and alignment jigs to position each panel flush with adjacent surfaces. Gaps were filled using precision welding techniques, and joints were ground flat to ensure a continuous, flat hull surface. Access scaffolding surrounded the hull, allowing welders and inspectors to work simultaneously at multiple levels. Non-destructive testing was performed along each weld, especially at high stress points near the bow and stern. With the side hulls in place, work began on the upper hull blocks and main deck modules. These form the uppermost structural level of the ship and contain the walkways, hatches, ventilation ducts, and bases for future superstructure components. A crane lifted each upper deck block into place. Like the lower blocks, these modules were fitted with internal bulkheads, stiffeners, and platforms. They were carefully aligned using deck markings and laser tools. The deck edge joints were beveled for welding, and each joint was filled in layer by layer. After welding, the surfaces were ground and inspected to verify smooth transitions and structural continuity. These blocks provided flat weather decks and stiffener attachment points for the ship's four masts. The final structural units are installed at the fore and aft ends of the deck, forming the bow and stern deck outlines. They include stiffening frames to support the bow and aft deck features. Before final welding, the structural units are checked for torsion, angles, and mating surface contact. Workers apply high-strength structural welds and cross-bracing where necessary. After all 38 units are successfully joined, the structure becomes a single unified hull. Internal bracing is completed and access points are sealed. Temporary supports and trusses are removed. Surface treatment and structural testing. After the hull structure is fully assembled, its entire surface is prepared for painting. Workers blast the steel with an abrasive to remove mill scale, weld residue, and contaminants. This process also creates a clean, rough surface for coating adhesion. After spraying, an anti-corrosion primer was applied to the entire hull. Tank spaces were further coated with a protective coating suitable for fuel and ballast water conditions. Inspection teams verified the thickness and uniformity of the coating. These efforts reflect Peru's growing naval and civil maritime capacity, integrating local needs with modern shipbuilding technology. The shipbuilding process at SIMA's Chimbote and Iquitos operational centers includes the construction, repair, and structural modification of various vessels. These range from the BAP Union sail training ship and the multi-purpose LPD-class vessel BAP Pisco to specialized ships like the salvage tug BAP. Morales and river gunboat BAP Castilla. The facilities also build social action platforms for remote areas such as Puno and the Putumayo River, supporting government outreach. Additionally, SIMA produces fuel barges, hopper barges, cargo barges, and river transport boats. Notable projects include tugboats, Magdalena and Medichin, and river cruise ships. Hyundai Heavy Industries combines creativity, innovation, and advanced technology to build the world's top-quality ships. Starting in 1972, Hyundai transformed Mipo Bay into a global shipbuilding hub. With vast facilities, expert engineering, and diverse ship types, Hyundai Heavy Industries delivers excellence through constant innovation and skilled craftsmanship. MSC Meraviglia, the flagship of MSC Cruises, is a next-generation cruise ship built in France, blending advanced technology, luxury, and elegant design. With a 4,500 passenger capacity, it features a 480 square meters LED sky dome, expanded MSC Yacht Club, and multiple entertainment areas, offering unforgettable voyages worldwide. Over 60 workers from the El Greco ship repairs team carried out around-the-clock operations to repair extensive grounding damage. The team began by assessing the 100-meter hull damage and preparing the affected area. Damaged plates were cut and removed using flame-cutting tools. New steel plates were then carefully aligned and welded into place along the hull side. Simultaneously, structural components such as frames and internal supports were examined. Where necessary, internal reinforcements were welded or replaced to restore structural integrity. Multiple welders worked in coordinated teams, using advanced welding techniques to ensure watertight seams. Cranes and lifting equipment assisted in maneuvering heavy steel sections. Throughout the process, quality checks were conducted to verify alignment and weld strength. The team continued day and night until the full length of the damage was restored, ensuring the vessel's seaworthiness and structural safety before it returned to service. The Uni-Hull 332 barge is launched by gradually sliding it down a slipway using controlled winching. Workers monitor the descent closely, ensuring proper alignment. As the barge reaches the water, it floats steadily, completing the launch process. Tugboats are then used to stabilize and maneuver it. The SIMA Iquitos Operations Center builds PIAS vessels to deliver essential government services to remote communities. 4 PIAS operate in the Amazon, while 1 class serves Lake Titicaca in Puno. These mobile platforms provide healthcare, banking, and social programs to improve living conditions in Lisnave Shipyard, strategically located in Portugal, spans 1.5 million square meters and is equipped to handle all types of vessels. The yard features 6 docks including Dock 20, 21, 22, 31, 32, and 33, as well as a hydrolift and 8 berths totaling 1,350 meters. Lisnave offers a wide range of services such as tank cleaning, slops treatment, and repairs to machinery, turbochargers, propellers, steel structures, piping, and electrical systems. Surface treatment and strict quality control ensure top performance. The shipyard is ISO 9001 and ISO 14001, certified by LROA, and complies with ISPS standards. With a strong focus on continuous training, safety, environmental responsibility, and customer satisfaction, Lisnave remains a global reference in ship repair and maintenance. 2 tugboats, Rawabi Freedom, were launched using a large crawler crane. Each vessel was lifted by multiple slings connected to the crane's hook. The crane carefully rotated and lowered the first tug into the water. Once stabilized and floating, the crane retrieved the slings. The process was then repeated for the second vessel, ensuring precision and balance during every step of the launch. Lisnave Shipyard successfully carried out 5 bulbous bow replacement retrofits on Hapag-Lloyd container vessels. The process involved cutting off the existing bow section and installing a newly designed bulbous bow, optimized for each vessel's speed and draft. These retrofits, completed on the Delaware, Colorado, Potomac, Missouri, and Hudson Express, aimed to improve fuel efficiency and reduce emissions by re-optimizing the hull form for current operating profiles. The shipbuilding process at SIMA's Callao and Chimbote operation centers. It begins with design and planning, followed by steel cutting and hull construction using modular block assembly. Each block is outfitted with systems before being joined to form the vessel's structure. Specialized sections are integrated for fishing vessels, such as F/P Incomar I, EPPSI, and EP Bramar 8. Technicians install propulsion systems, piping, and electrical components. The vessels, including EP Guayatuna Uno, Bravo 10, Patricia, and Tasa 55, undergo rigorous fitting-out stages. The azimuth tugboat is also shown under construction. Final steps involve painting, sea trials, and delivery, with continuous support from SIMA's Departments of Naval Repairs and Electronic Innovation. Ceramax demonstrates its hands-on training approach for welders. Trainees begin with classroom sessions, then move to practical exercises on welding simulators and real machines.
Okay, stop.
Under expert supervision, they learn to operate advanced orbital and mechanized welding equipment, practicing on mock-up joints resembling real project conditions. The instructors provide detailed guidance on machine setup, welding parameters, and torch control. Throughout the training, emphasis is placed on safety, precision, and consistency. Trainees are gradually exposed to different welding positions and pipe sizes to build versatility. This method ensures welders gain both technical competence and confidence before deployment to actual work sites. The training aligns with Ceramax's high standards, aiming to develop a capable workforce ready to deliver quality welds across complex projects in energy and infrastructure sectors. The cutting process of thick steel plates using the 2015 ESAB plasma cutter. First, the operator loads a large steel plate onto the 15 by 3 meter cutting bed. The CNC-controlled cutting head, equipped with a high-definition plasma torch, moves precisely across the plate. As the cutting begins, the plasma arc pierces through the steel, producing clean and accurate cuts, even on plates up to 40 millimeters thick. The machine performs both straight and complex bevel cuts, with chamfers reaching angles of up to 45 degrees, thanks to its 5-axis beveling head. During the process, the Vision CNC system automatically manages gas flow and cutting parameters, ensuring consistent quality. The torch moves smoothly over the entire 24,000 by 6,000 millimeters work area, cutting out shapes with minimal dross and high-edge precision. The video also shows the machine marking reference lines on the plate, demonstrating its plasma marking capability. Finally, the cut components are removed from the bed, ready for further processing. The machine delivers high-speed, automated, and precise cutting, suited for heavy-duty industrial applications. The process begins with steel block assembly. Large, prefabricated hull sections are positioned in the hull and meticulously aligned. Workers weld the panels into uniform blocks, forming the ship's basic hull segments. Once complete, crane operations lift each block into its designated slipway position, carefully lowering them onto keel blocks. Next comes the module joining stage. Sections are tightly butted and welded together. Welding robots and heat inspections ensure pristine seams. Scaffolding encircles the growing structure, while electricians and pipe fitters begin installing internal systems, wiring, piping, and ductwork, all coordinated alongside welding. With the hull fully assembled, surface preparation begins. The exterior is grit blasted, and multiple coats of primer and paint are applied using spray booths, protecting against corrosion. Then the ship is rotated for deck outfitting. Massive deck plates are lowered and welded in place, forming the ferry's upper structure. Interior outfitting follows. Bulkheads, cabins, and machinery spaces take shape as workers install insulation, panels, and equipment. Engines, generators, and pump systems are craned on board and precisely secured to foundations. The vessel is continuously inspected. Ultrasonic testing checks weld integrity, while alignment jigs ensure everything fits accurately. Finally, launch preparations. Supporting blocks are removed and the ferry is slowly launched. It glides off the slipway into the water, concluding the time-lapse sequence of hull assembly, outfitting, and launching. Icon Yachts, founded in 2006 in Harlingen, the Netherlands, specializes in building and refitting high-end superyachts. With direct sea access, a deep dry dock, and advanced facilities, Icon delivers custom yachts quickly and efficiently, blending innovative design with exceptional craftsmanship. At Haydarpasa Port in Istanbul, a 36-meter-long, 8.55-meter-wide firefighter boat, weighing 220 metric tons, was carefully lifted by a large crane and placed onto a sea river vessel operated by CT Logistics. The heavy lift operation was performed with precision to ensure stability and safety. Once securely positioned on the barge, the boat was fastened for transit. The vessel then departed, heading across the Caspian Sea. The final destination for the shipment was the Turkmenbashi International Seaport in Turkmenistan. The construction of the BAP Union, Peru's first sail training ship, was a monumental project carried out entirely by SIMA Peru between 2012 and 2015. This four-masted bark, now one of the largest of its kind in the world, was envisioned to train cadets from the Peruvian Naval Academy and act as a traveling ambassador for the nation. The project officially began on December 8, 2012, with the keel laying ceremony attended by the President of Peru. Designed by Spanish firm CYPSA, the ship was built from 38 large steel blocks. By the end of 2014, the hull was completed and launched into the sea during a ceremonial blessing. Government officials, naval officers, engineers, and workers celebrated the moment as a historic achievement, highlighting the craftsmanship of Peruvian hands. In 2015, construction continued with the installation of the four masts, the propulsion system including a Caterpillar diesel engine and Berg variable pitch propeller, and interior structures. Spanish company Acopafi, in collaboration with MO Contract, handled interior outfitting. Navantia provided an integrated control, navigation, and communication system. The ship was fitted with 34 sails covering over 3,400 square meters. A bronze figurehead representing Inca Emperor Tupac Yupanqui was mounted on the bow. The vessel also features classrooms, a library, and navigation labs, supporting instruction in celestial navigation, meteorology, and naval operations. After completing sea trials in mid-2016, the BAP Union was officially commissioned into the Peruvian Navy on January 27, 2016. That July, it embarked on its first international training voyage. The BAP Union stands today as a symbol of national pride and perseverance, representing Peru's naval heritage across the world's oceans. It is the largest training sailing ship in the Americas, built entirely in Peru by its own people.